மெதுவா எங்க போறோம்னாக்க அடுத்த பாடப்பகுதிக்கு போறோம். மெதுவா கவனிங்க. செமிகண்டக்டர்னா அதனுடைய இம்பார்ட்டன்ஸ் என்ன? செமிகண்டக்டர் அப்படின்றது கண்டக்ஷன் ஆஃப் எலக்ட்ரான்ஸ் வச்சிருக்கு. இந்த எலக்ட்ரான் கண்டக்ட் பண்ணணும்னா ஒரு எனர்ஜி லெவல்ல இருந்து இன்னொரு எனர்ஜி லெவலுக்கு தாவணும். அப்ப நமக்கு ரெண்டு விதமான ஸ்பெக்ட்ரம் கிடைக்குது. கண்டினியூஸ் ஸ்பெக்ட்ரம்னு ஒண்ணு கிடைக்குது, லைன் ஸ்பெக்ட்ரம்னு ஒண்ணு படிக்குது. நியூட்டோனியன் மெக்கானிக்ஸ் ஒண்ணு படிச்சிருக்கோம், கிளாசிக்கல் மெக்கானிக்ஸ் ஒண்ணு படிக்கிறோம், குவாண்டம் மெக்கானிக்ஸ் ஒண்ணு படிக்கிறோம். இவைகள்ல போர் ஆட்டம் மாடலை எடுத்துட்டு ஒவ்வொரு எனர்ஜி லெவலுக்குள்ள டெரிவேட்டிவ் பார்ட்டை எடுத்து அந்த எனர்ஜி லெவலுக்கு வரக்கூடிய ஸ்பெக்ட்ரல் லைனை ப்ரூவ் பண்ணிட்டு பிறகு பவுலிஸ் எக்ஸ்க்ளூஷன் பிரின்சிபிள அடாப்ட் பண்ணி குவாண்டம் ஸ்டேட்ஸை சொல்லி எலக்ட்ரான்ஸ் ஃபில்லப் ஆகிறத சொல்லி அடுத்த ஸ்டெப் என்ன பண்ணியிருக்காருன்னா நிதானமா ஒரு ஆட்டமா இல்லாம ஒரு வேப்பர் ஸ்டேட்டா இருந்தா என்ன ஆகும், ஒரு சாலிட் ஸ்டேட்டா இருந்தா என்ன ஆகும்னு சொல்றாரு. மெதுவா நம்ம பேண்ட் தியரி நோக்கி நகர்றோம், பார்க்கலாம்.
So in the previous lecture we discussed about multi-electron atoms where any particular electron finds itself in the potential of the nucleus, positively charged nucleus, and the rest of the electrons. So it's no more a Coulomb force, it's no more a Coulomb potential, but then this whole complicated potential can be equivalently represented by some kind of an average central potential. And if you take that approach, then you still have that Schrodinger equation with a central potential minus h cross square by 2m del square. This is the kinetic energy part, kinetic energy operator we call it, and then this equivalent central potential, and this is equal to E psi. And the only difference from hydrogenic kind of levels is that now energy depends on N as well as L. So you have those states 1s, 2s, then 2p energy is different from 2s energy. It depends on L, and then 3s and all those things, 4s, 3d, 3p, all those things. And then we talked about aggregation of atoms, as in the case of a gas or in the case of a vapor, where you have identical atoms. For each atom, the energy levels for the electron is given by this equation, is given by these energy levels. But then there are too many atoms, and each atom will give the same energy level but more number of quantum states. And if there are capital N atoms, then we have 2n quantum states here, 2n quantum states here, 6n quantum states here, and so on. So these things we discussed. And then we are more interested in what happens if these atoms are brought closer to form a solid. So there are various approaches that one can take to understand the modifications in this energy level scheme. If you just talking to someone whom you want to tell the things qualitatively, one idea is that if these atoms come closer, like this, then an electron not only sees the potential of its own nucleus and the rest of electrons in that atom, it also interacts with the other nuclei and the other electrons. And therefore this potential energy, that interaction is no more given by this kind of central potential, and therefore the energy level has to be changed. And since you have large number of atoms, the environment of an electron here in this vicinity, an electron in some other vicinity, all those things may not be identical, and therefore for some of the quantum states the energy may go up, and for some of the quantum states the energy may go down. So if you have a sharp energy level, let's say this one, let's say this is 3s, again if I go for that sodium where Z is 11, then you remember that 2 of the electrons will go here, 2 will go here, 6 will go here, and 1 will go here. And if you have large number of sodium atoms as in a sodium vapor, then this will be, all these 2n quantum states will be full, this will be full, this will be full, and here you will have half the quantum states occupied by electrons and half the quantum states empty. So if you take that 3s, now the sodium atoms are interacting with each other. It's making a solid, a crystalline solid with some kind of a crystal structure. So all these interactions have changed the energy level. So all those 2n quantum states which were here, for some of them energy is going up, for some of them energy is going down, and therefore so these 2n quantum states will have now these energies, different energies. And this whole energy difference here or energy range here can still be in electron volts. Okay, this can still be in electron volts, few electron volts. So that's the kind of typical energies. Remember, for hydrogen atom it was minus 13.6 electron volt, and then minus 10.2 electron volts, and so on. So that's the kind of scale for energy in atoms and molecules and solids. So this can still be in electron volts, few electron volts, but the number of quantum states here could be some 10 to the power 23 or so. If you take 1 mole for sodium, this will be some 23 grams. So if you take 1 mole, you have Avogadro number 6 into 10 power 23 atoms. So capital N is that. So these many quantum states in few electron volts. So the average separation between the consecutive quantum states energies will be hardly 10 to the power minus 22, 23 electron volts. 10 power minus 22 electron volts, and therefore this will just appear as a continuous band of energies. So all energies in this is there somewhere here or here or here, because that gap is so small, 10 power minus 22 minus 23 eV. So the sharp energy levels are split in bands. Okay. Similarly, you have 2p, so 2p will give you another band here, 2s will give you another band here, and so on. Obviously, if you look for that inner electrons, core electrons, then they are much less interacting with the neighbors because they are inside, and therefore these bands will be much more narrow. 1s, 2s, maybe this splitting and this spread is very, very small, negligible. You can still consider these to be almost sharp energy levels, but the outer ones, they will certainly do a lot of spreading. If you look at this 3p, this 3p is also there, so this 3p will also spread, although there is no electron here. Normally there is no electron here in 3p for sodium, but then the energy levels are there, the quantum states are there, and because of this interaction, because of this change in potential energy, this will also spread out. So this is one way qualitative understanding. You can go a little ahead to be more sophisticated, and you can come through that chemistry point of view, how molecules are formed. how hydrogen molecule is formed. Two atoms coming close to each other, what happens to the energy levels? So one can start with molecules, the two atoms coming close to, and then generalize it to capital N atoms coming close to each other. So you know, if you take a hydrogen gas in a gas jar, in school days you must have studied how to make hydrogen gas in laboratory. You put some zinc pieces in some bottle, some wolf bottle having two these necks, and then you pour dilute acid on that hydrochloric acid or so, and then you get that hydrogen gas which you collect in a gas jar and so on. So if you take a hydrogen gas, this is the diatomic gas. So two hydrogen atoms come close to each other and make this molecule. And these molecules are widely separated from each other and going into that vessel. So what happens to the energy levels of this system, this molecule? So for hydrogen, you have all those energy levels. One is both, if it is in ground state, in both these atoms, hydrogen is in 1s. So if this is 0, energy 0, this is minus 13.6 eV, and this is 1s. For the other atom also, you have the same energy, minus 13.6 eV, 1s. So that electron is here, and this electron is here. Spin could be in any of the state, plus half or minus half. Now if they are brought closer, what happens? So the corresponding wave function here is, let us say, psi 1 r, and here it is psi 2r. What is the difference? Both had 1s. So this functional form is same as this functional form. Only thing is that this r is measured from the nucleus of the first atom, and this r is measured from nucleus of the second atom. So, but the functional form is same, one is wave function. So that functional form will be the same. Now when they come close and two hydrogen atoms they form a single system, how do I write energy of this? So there are mathematical procedures to solve the Schrödinger equation in this particular case, and exact solution could be very, very difficult. But then there are methods to get almost very nice results, and one is called what is LCAO. This is known as linear combination of atomic orbital. Where you assume that the wave function is given by some linear combination of these two atomic orbitals, atomic wave functions. So you have a wave function here, you have a wave function here, refer to one origin, refer to other origin. So you have two wave functions, and then you make linear combinations of them, and then see what linear combination gives you fixed energy, definite energy in case of this interaction. So now this interaction is different, potential energy is different, slightly different from the earlier one. So use this wave function and then use Schrödinger equation and then do the mathematics to get what is this C1, what is this C2. And people find that if you do all these things, if the original energy is this E naught, original energy is E naught for each atom minus 13.6 eV. You get for this interaction two possible energies, E naught plus delta and E naught minus delta. And for this one you have one kind of combination which sometimes people say sigma star or so. Okay, how do I write? So there is one kind of combination, let me call it A, and this, for this you have another kind of combination, let me call it B. This psi A turns out to be 1 over square root of 2, and then you have this psi 1r and minus psi 2r, and the psi B turns out to be 1 over root 2 and then psi 1r and plus psi 2r. Okay, so this kind of combinations give you definite energies, and those definite energies are one up and one down. So here if you plot in this diagram, one energy goes up, so this was identical energy, then one energy goes up, one energy goes down. This is that psi B, and I have written B for bonding. And for this the wave function is psi A, and this A is for anti-bonding. You still have 4 quantum states. You had 4 quantum states. You had 4 quantum states, 2 quantum states here, 2 quantum states here. And again you have 2 quantum states and 2 quantum states. So the number of quantum states remains same, but then energy, which was just minus 13.6 eV when the atoms were far apart, now the energy is split in 2 parts. One is this anti-bonding where the energy has gone up, and one this bonding where the energy has gone down. And therefore in ground state, to minimize the energy, both these electrons will be in this state. Okay, both the electrons will be in this state. One spin down, one spin up, that means plus half and minus half, so that the Pauli exclusion principle is respected, and these two are empty. Okay, this is called bonding because these are the electrons which keep this molecule bound. The wave function is symmetric. The wave function is symmetric, and it's a some kind of an overlap here. So you have some kind of electrons which are more close to these nuclei, and it's a bonded molecule. Whereas if electron goes here, the energy goes up, and it's antisymmetric. So at center you have much less population of electron, much less probability of electron being here, and the electrons are far apart, and therefore it doesn't bind that system. So this kind of splitting is there. You must have done these things in your +2 chemistry classes. So this is why hydrogen is in the diatomic molecular form. What happens if I have helium? If I take helium gas, you know, is monoatomic. Helium does not form 2 heliums, 1 molecule, it doesn't form like that. Helium gas is monoatomic. Why? You can understand from this. In helium you have 2 electrons, and both the electrons are in 1s. Both the electrons are in 1s. So if you have 2 helium atoms, you have 2 helium atoms, let us say, then you have 2 electrons here and 2 electrons here. 4 quantum states, 4 electrons. And therefore the splitting is there. If you solve this Schrodinger equation, you will still get this splitting, but then all those 4 quantum states will be occupied by the 4 electrons. So 2 electrons will be here, 2 electrons will be there. No gain in overall energy. In hydrogen case, if one electron is here, another electron is here, it's minus 13.6 and minus 13.6. But if both the electrons come here, the energy is lowered, and therefore it gives rise to the stable configuration of the molecule. But in helium there is no gain. There is no gain here, and therefore these atomic orbitals are equally good, and therefore it doesn't go for this bonding. It's not diatomic. So these kind of things are there. Now extend this concept. If 2 atoms come close to each other, because of this interaction, they are identical atoms, but because of this interaction, the energy levels are split in 2 parts. And similarly, if 10 to the power 23 atoms come close to each other, then that energy level will split in those many parts, and it will form a band. It will form a band. So this is another approach through which you can understand that. And then there is yet another physicist approach. You can also write the Schrodinger equation from this whole crystal. So you have an electron, and that electron finds itself in the potential of all those atoms, all those nuclei which are sitting there together with their core electrons. So ions are there, rest of the electrons are there, and so on. And since crystal is a periodic structure, in crystal the atoms are arranged in some very well regular patterns. So this potential energy function for an electron is also a periodic potential. And if you have periodic potential, and then you have a wave function, you want to solve the Schrodinger equation in that periodic potential, then you do get some wave functions which are also periodic with the period related to the period of that potential. And if you do that algebra, then also you get the similar result, that depending on the momentum, depending on what value of momentum is there or wavelength is there in that wave function, you will have energies. So energies are related to the momentum, and then there are certain energy values where you do not have any allowed quantum state, any allowed energy level, and then you have continuous variation of energies for different cases. So for any given momentum, you have a continuous energy band, and then maybe some gaps are there, again you may have some energy bands, and so on. So whichever way you go, you end up with the result that if the atoms are brought closer to each other so that the electrons start feeling the presence of other atoms, other electrons of other atoms, other nuclei, then these sharp energy levels are split into energy bands. And how much will be the splitting, etc., for how much will be the splitting for 2s, how much will be the splitting for 2p, how much will be the splitting for 3s, all those details will be different for different atoms, different kinds of atoms. Z value will determine all those things. So the diagram which we drew for energies is now modified. So in solids, the energy levels, when they are split and they form bands, you may have this kind of structure. Suppose this is your lowest energy level, which has hardly spread, and then you have more levels corresponding to those inner cores, which are again very slightly broadened, but then you may have bands, energy bands. These are all energies that I am showing here, energy going this way. So all these energies are allowed here. So this band is this much only, this is this much only. Then as you go up, the bands are more spread out. Nothing in this direction, okay, nothing in this direction. It is only one dimensional diagram. So energy is just energy, and one can count the levels, number of levels, number of quantum states and so on. So this is how it can be. Now that means if I look for energies, we have these gaps, and then we have these allowed energies. Initially also we had gaps. Initially when the atoms were far apart, then also we had sharp energy levels, and all these were gaps, So either this energy is allowed, or this energy is allowed, or this energy is allowed, or this energy is allowed, and so on. But now the gaps are still there, but then this allowed thing, which was a sharp level here, is now a range. All these energies are allowed. You have quantum states with these energies almost continuously distributed. Here also almost continuously distributed. Okay, so that's the kind of structure. This is at a certain interatomic separation. At room temperature, let us say, where we do a lot of our work, this solid has a certain interatomic separation, some kind of a lattice structure, some kind of a lattice parameters are there, A, B, C, alpha, beta, gamma, and all that. So with that, this kind of thing will result. Okay, if that separation is a little bit disturbed, thermal expansion or anything, then this diagram will widely vary. It can vary. Okay, so this is the kind of thing. So now we have enough preparation, and we can discuss why certain material are electrically conducting, why certain materials are insulators, and why some materials are semiconductor, which is the focus of all this course. So all these properties of different materials can be discussed in terms of this band diagram.